A residual is the difference between the actual score that we've observed and we've used as the basis for a regression and the predicted value of the regression. So on a graph, it's very easy to understand the idea of a residual because basically we have our trend line based on our correlation, which kind of tells us, well, what's the linear trend for the data by best fitting it. But most of those data points do not fall directly on the line, and they're a distance apart. So you can kind of visualize each residual as the distance from the line on the y value. So I'll draw those in I guess green or something, but each score has a particular residual, and that just is how far away from that averaged line did it end up. So looking at the definition from our textbook, it says residual is equal to observed y minus predicted y. Or again, using the notation, it would always be y minus y hat. Remember, this y hat is used in a linear regression. Actually, I forgot to write that on my equation for before, so let's fix that because that was very bad of me to have done. But I want to be careful whenever you see y with the little caret hat. That's always implying it's a regression line, not necessarily, which means it's used for prediction. It's calculated via correlation and least squares regression. Another actually thing that's interesting is, why is it called regression line? Shouldn't it be, figuring out what we're expecting? But usually trends that are extreme outliers tend to regress towards the mean, and that's where that's the origin of the name for regression. Regression often has the connotation that you're getting worse, but it's sort of like more towards averaging out. And the line, if you can follow the line to the mean, which is kind of where the term was coined from. Not necessarily a perfect name for this process, but it is what it is. But let's calculate some of the residuals. So to find the residuals, basically you would just take your known data points y and subtract from the predicted value. So let's say we wanted to do this for one of the data points. We could write this as y1 minus y hat 1. And basically I would just need to know, well, what was my first data point? Y1 would be the first value of her quiz score. So she scored 100. And basically we want to know, well, what's the difference between that and her actual what would be the predicted value of her quiz score in that case? So and if we're looking at the data point, that would be right here, right? This is her score where she got 100 and she spent 3.5 hours studying for that. But essentially that value is much higher than her predicted score, which would follow along the red line. So if we want to know, well, what would be her predicted score, we'd need to plug 3.5 into our line, because the line follows this equation that we found. And if we plug in 3.5 for x, basically you plug in the associated x value into that. Basically, we know that y hat is always equal to 9.34 x hat plus 59. And this again would be for the first data point. And I don't need to use the hat notation there. That would be improper. Okay. And so we know that x1, that's how long she spent studying for that quiz, which was 3.5 hours. So this will give us our expected value for her quiz score based on our regression. And so let's go ahead and pop that into our calculator. 9.34 times 3.5 hours studying plus 59. And we would get an expected value of 91.7 in this particular case. So basically she got 100 on that particular quiz. That's higher than her expected score. So if I take that difference, 100 minus 91.7, that would be approximately 8.3, and that would be her residual for that particular score, which just basically means it's higher than expected. But it happens. And we could do this again for other scores. Let's say for one that's very close to the line, let's just say this point right here. She spent 4.5 hours studying and she got a 99. That one, just based on observation, looks to be close. Let's see what the residual would be for that one. So that was her her sixth quiz score, so let me go ahead and write that down. I'm just sort of picking random scores here. Obviously, you could calculate all the residuals if you wanted to, but that's pretty tedious. And so, yeah, her sixth quiz score was a 99, and the expected value should be based on how long she spent studying, which was 4.5 hours. So it'd be 9.34 times 4. Sorry, I already lost my place here. It would be she spent 4.5 hours. So times 4.5 plus 59. And again, I'm just using my least squares regression line to predict the value that we'd think she would get. So that would be 9.34 times 4.5 plus 59. That would leave me with a predicted score of 101.03. Let's just say 101. And that might seem strange because usually you don't imagine having scores higher than 100. And that's just because our line, it does not stop when you get to 100. Like, let's say she spent 10 hours studying. Our predictive line would predict that she's going to get like 150 score or something like that. And this is just an important thing to note about regression, is that you never want to use it for values that are exceedingly outside of the data that you use to predict the line, because it might not and probably won't necessarily hold if you go much further away. So if I doubled the amount of time studying, it's not necessarily going to continue following a linear progression. But anyways, in this case, that would be 99 minus 101, and we see that she would have a negative residual here. The residual would be -2, meaning that she really scored 2 under her predicted outcome. And a residual plot is just a graph of all the residuals on the x-axis. So each one of those data points has its own residual, and this gives us a sense for how far away. It's kind of like if you imagine taking the data, instead of looking at it on a slanted line based on the slope of the least squares regression line, if you just flattened it out and took each point, how far away each point is from its residual, you would come up with a residual plot. Like for y1, she spent 3.5 hours studying, and that's we can see that one of those data points we calculated the residual to be 8 would be right there. That's all that means. And then when she spent 4.5 hours studying, she had a residual of -2. But it gives us a sense of how far away her points were from the mean or the average. And she had 3 scores that were above the average and fairly far above the predicted outcome, and some that were below. All at the end of the day will best fit to the line itself. Now, the last thing I wanted to talk about, might as well just get it done within this video rather than doing another video, is what's called a lurking variable. And another big idea and something to be very careful with when analyzing things with statistics is that association or correlation does not always imply causation. It's a very overarching theme in stats. But like when we determined that the correlation was 0.929, what we said is that was very strong correlation, which means that her time spent studying directly relates mathematically to a higher quiz score. But that doesn't imply that study time 100% reflects what quiz score you get. It's not causation. So she can't conclude that more time that she studies will guarantee a better quiz score. It just means it's going to be more likely. And there might be a lurking variable is just the idea that there's actually a different variable that could be more of a direct link to quiz score. Like, for example, this time spent studying has no indication of, well, how well was she studying? Like, was she studying very, very intently, or was she sort of being half paying attention, was she multitasking while she was studying? It doesn't, that could be a different variable at play, which is, well, how focused was she during her studying on a scale of 1 to 10? Or another thing would be those quizzes. Those quizzes weren't all necessarily the same thing. Those could have been on different subject matter, some of which might have been much harder and much easier. So there could be other variables at play. That's kind of the idea of lurking variables, and why you don't always want to assume just because I've found something which is strongly correlated, like in this case we did get strong correlation, it doesn't mean that it is what's causing the outcome to happen. And so, just to sketch some other lurking variables in this case, we could have something like the quality of her study. Or we could have the difficulty of the quiz. Or, another thing would be how was the professor in a good mood or a bad mood when she was grading the quiz at the time, assuming that affects the outcome. There could be a number of different things that are also affecting these relationships, and which is why we shouldn't jump the gun in saying that we exactly know what's going to happen in the future. But we can say with pretty good certainty that in this case, there is correlation between how long she spent studying and how well she did.